Now let's have a closer look at these results. We have some good news for you and some bad news as well. The good news are that the algorithm seems to work very well, getting a very nice deblurring outcome. The bad news are that things are not behaving along the lines we expected. Here is what I mean by that. This is the function we are minimizing. And now let's look at the residual as a function of the iterations. This residual is the second term in the function f of alpha, the L2 distance between the given image z and h times d times alpha. This residual should have been the noise level, square root of 2. Instead, in all the algorithms, it leads to a smaller value. Why? Because we did not set lambda properly. We need a bigger lambda so as to tune the residual to match the noise energy. However, in doing so, we will not get the 7 dB improvement anymore. As it turns out, this is the least of our problems. Let's ask a very strange question. Is the resulting alpha sparse? Here is our major difficulty. This graph shows the cardinality of alpha as a function of the iterations for ista and fista. We do not bother showing you the SD results because they tend to be denser. The black line marks the number of pixels in the image, which is about 65,000. As you can see, the results are not sparse at all. Moreover, if we stop after 60 iterations, the number of non-zeros is about 140,000 elements, much more than the number of samples in our signal. For a solution to be sparse, we should expect a value smaller than 65,000 non-zeros. So what is going on here? Well, one thing is clear. Our optimization must result with a sparse solution, and this means that we should have run the algorithms much longer to get to these optimal results. Clearly, if we want to get sparse solutions, we must run the algorithm with many more iterations. Let's do just that and see what we get. In fact, this time we will do this while increasing lambda to be 0.17 so as to get the desired residual. If you are wondering where this value comes from, it was found empirically by trial and error. So we summarize this experiment and its results. We ran fista for 200,000 iterations with this new value of lambda. The solution we got had about 18,000 non-zeros, so it is indeed sparse. The residual is near perfect, and this ratio shows that all these extra iterations gave a descent of 1.5% in the function value. What about the result? How good is it? The ISNR stands now on 3.77 dB, which is much worse compared to what we got before. The main question all this leads to is this: how come we got so good result for a dense alpha? In this slide, we present the results of the above described experiment. In this graph, we show the residual value as a function of the number of non-zeros as the algorithm iterates. The blue curve refers to the original value of lambda, and as can be seen, we slowly converge to a residual that is simply too small. The red curve stands for the updated lambda, and now the residual goes to the proper value. The second graph on the right presents these two runs, this time showing the ISNR as a function of the number of non-zeros in the solution. The solution starts dense and slowly gets sparser and sparser. However, the peak performance is obtained for the wrong value of lambda and for too few iterations where alpha is not yet sparse at all. And here is the image we actually get after 200,000 iterations and for the sparse vector alpha. Observe the background region in the image, where there are strong artifacts. Still, one has to say, this result is not bad compared to the image we started with. How can we explain this bizarre behavior? Well, on the positive side, the SparseLand model seems to work fine. We merged this model into our deblurring problem, minimized this function properly, and got a reasonable result. This is as far as good news go. The bad news are that things behave strangely. While minimizing the above function, and with the wrong value of lambda, we got a far better result and for a solution that has quite a dense representation. How come? The answer to this riddle is quite complicated and has several facets. First, we will see in a following chapter that dense representations do emerge sometimes as better, being connected to the minimum mean squared error estimation. Another explanation refers to the connection to a special case of the SparseLand model, the CSC. We will not have time in this course to discuss the convolutional sparse coding model, CSC for short. As it turns out, everything we did here is closely related to this CSC, for which things behave differently. A third explanation for what we have seen has to do with global versus local modeling. We will get a taste of this issue in a later chapter when we discuss image denoising. Above all these stands the following intuitive explanation. In order to restore an image, one needs an averaging effect. Choosing the fewest possible atoms to represent the result image implies lack of such averaging. Getting several possible sparse solutions and merging them does make sense, since it will smooth things out, just as we saw in the background of the better deblurred image we got. So we leave this puzzle open for now, and we'll meet various aspects of it as we proceed into other tools and applications in this course. Our next main emphasis is going to be the choice of the dictionary D, which is clearly key in a proper use of the SparseLand model.